linear combination, set of vectors, and so on. So I started by defining a set of vectors, and I had a special notation for that. So today we are going to look at specific things like so basis and dimension of a vector space or a subspace, and rather than just giving definitions, I want to give some examples today, so that why these ideas are being pursued should become a little bit clear. Why we are looking at these funny spaces? Why don't we look at a set of all continuous functions and then call it a space? Or why we want to look at a set of polynomials and call it a subspace? So yesterday we had developed this notation. This notation was a set S, let's say, was defined as xi, where I is equal to 1, 2. This could be a finite set in some situations, it could be an infinite set. I am currently defining a finite set of n vectors. This means there are n vectors. S belongs to some vector space. So X is my vector space, and S is a subset of X. S is a subset of X. Here, one way of one example that I gave was from R5. So I said that you have two vectors, say x1. This was 1, 2, 3, 4, 5, and x2, which is 5, 4, 3, 2, 1. I'm putting some arbitrary two vectors from R5. So I can define a set S, which is x1 and x2. These are two elements in this set. Where S is subset of R5. Okay? S is a subset of R5. In some cases, I would define a set S to be set of polynomials. I define the set S, which is set of polynomials. So my first vector here, x1z is 1, x2z so in this particular set, I have n plus 1 vectors. Which are denoted like this. This is the first function. This is the second function, x2z, second vector. Okay, this is the third vector. This is the n plus 1 vector, and so on. So the notation here is generic. It could be used in the context of n-dimensional spaces. It could be used in the context of function spaces. It could be used in the context of polynomials. Depends upon what context you are looking at. Okay. So that is first thing. Then yesterday, just a quick review, we talked about linear combinations. So f is my field, and if I take some scalars, say alpha 1, alpha 2, alpha 3, which the scalar set, this belongs to f. If the scalar set belongs to f, then we define a vector which is linear combination of the original vector. So I can construct a new vector x, which is alpha 1 x1 plus alpha 2 x2, and so on, plus alpha n n. So this linear combination in the later example where we took vectors as polynomials would be a nth order polynomial. Okay? Or n minus 1th order polynomial if it had only n. In the case of n dimension, it will be a vector in R5. Okay, I can talk about a new vector x, which is alpha 1, 1, 2, 3, 4, 5, and alpha 2, 5, 4, 3, 2, 1. When alpha 1 and alpha 2 are any two arbitrary scalars drawn from R. Okay, this is linear combination. And then we said that we have this notion of span of a set. Span of a set is set of all possible linear combinations. Span of S, which is many times denoted as square bracket S, is, so I take all possible linear combinations of elements of S, and then what I get is span of, if I take all possible linear combinations in this set, then what I get is the span of this particular set. We saw some examples in 3 dimensions. I took 2 vectors, I said span of these 2 vectors will be a plane cutting through the origin. Will be a plane cutting through the origin. If I take 3 vectors in the same plane, span will be again plane cutting through the origin. So it's not going to be different. Well, this sounds very abstract. Let's get down to some concrete examples which probably you have seen in your undergraduate, and then let's connect. Why do I need span? Why do I need to talk about subspaces? Where do we need them? And then we'll move on to this concept of linear dependence, and then talk about basis. Before I do that, let's get some concepts clear about the span business. So where do we need span? Why is it important? So something that we actually keep using all the time. These concepts are used when you solve linear algebraic equations, differential equations. You keep doing it unknowingly without understanding what is actually happening, because some of these concepts are not introduced in the undergraduate. Let me start with an example, which is simple solving linear algebraic equations. So my example 1 is, I want to solve Ax equal to B, where A is an invertible matrix. So I am taking one simple matrix here, 1, 1, 0, 0, 1, 1, 1, 0, 1 into x, that is x1, x2, x3, gives me b1, b2, b3. Gives me b1, b2, b3. Okay? Actually, this equation I can rewrite slightly differently. You will start getting insights into why I am talking about the span. I can rewrite this as 1, 1, 0 into x1 plus 0, 1, 1 into x2 plus 1, 0, 1 into x3 is equal to b1, b2, b3. Am I correct? I am just rewriting this equation. Here, B is a vector which is linear combination of first vector, second column vector, and third column vector. Okay? What is span of column vector 1, column vector 2, column vector 3?
Another column.
What is the span? The span of these 3 vectors I want to show is same as 3-dimensional vector space. What is span? All possible linear combinations. So all possible linear combinations, are these vectors linearly independent?
Yes.
Well, by inspection for this particular case, because you know about linear algebra, you can see that these 3 vectors are linearly independent. What will be span? What will be all possible linear combinations of 3 linearly independent vectors in 3 dimensions? Entire space. Okay, will be entire space. So I can write a solution which is x. This is A inverse B. Well, I'm not right now worried about how to compute A inverse. I suppose you know this. And this A inverse B turns out to be B1 times half minus half plus B2 times half minus half plus B3 times if I actually compute a solution of this system of equations, okay, you can do it very easily. Gaussian elimination, Gauss-Jordan method, you can compute inverse. Okay, I'm just rewriting the solution in terms of A inverse B, except that I have chosen to write like this. I have chosen to write like this. Okay, give me any B vector. I can write the solution like this. Okay, so where does the solution belong to? Solution belongs to the span of the solution X belongs to span of this vector, and this vector. Again, from undergraduate experience, you know that these three vectors are linearly independent. Okay, so the solution actually belongs to the span of these vectors. Okay. Now this is a well-behaved example. Matrix A is invertible. I am going to move on to another example where matrix A is not invertible, and I still want to find a solution. Matrix A is not invertible. I still want to find a solution, and then we will get this concept of the solution belonging to a space which is not R3. In this particular case, what is the solution space? So X belongs to span of half minus half minus half and half. The solution actually belongs to span of this all possible linear combinations, right? If you specify B, I'll get one particular X. How many ways I can specify B? Infinite possible ways. B1, B2, B3 can be chosen. All vectors in R3 can be put here. I'll get one particular solution. So this is an example where you have to look at a span. Now let's look at another example. Then the things will become more clear. Okay, I'm just going to change this matrix to a slightly different matrix. 1, 2, minus 4, minus 1, minus 2, 4, and 2, 4, minus 8. And then I'm going to look for a solution which is for 0, 0, 0. I'm going to look for a solution which is 0, 0, 0. Well, so basically I want to solve for 1, minus 1, 2, 2, minus 2, 4, and minus 4, 4, minus 8. This becomes 0, 0, 0. Is this matrix invertible, first of all?
No.
Why?
Linearly dependent.
The columns are linearly dependent. I just multiply this column by a factor, I'll get this. I just multiply this column by another factor, I'll get this column. Okay? Is this problem solvable? Is equal to 0?
Yes.
Why?
There are infinite solutions.
Why? I want why, not what.
Number of unknowns are lesser than equation.
Huh?
Number of unknowns are lesser than equation.
Number of unknowns are 3. 3 unknowns, 3 equations.
Linearly dependent.
There's only one independent equation.
Yeah, linear dependence. So these are linearly dependent and I should be able to get infinite solutions. How do I get them? So this matrix is non-invertible. So as the columns are linearly dependent, this matrix is not invertible. Can I find a solution? Can I find a solution? What are the possible solutions to this problem? So what about 2? Well, I am not interested in 0, 0, 0. I am not interested in trivial solution. What I want to know is, are there non-trivial solutions? Are there non-trivial solutions?
Yeah.
So tell me the solution. So what about x2 is equal to 2, x1 is equal to -1 and x3 is equal to 0. Will this form a solution?
Yeah.
Right? Multiply this by 2, multiply this by -1. Okay? I will get 0, the last column is multiplied by 0. Other candidate solution, of course, is multiply this by 4, multiply this by 0 and multiply. Right? I get two possible candidate solutions. I get two possible candidate solutions here. My first solution, well, remember, these are linearly dependent columns, which means there are same equations repeated again, multiplied by scalars. Okay? I am not taking the equation viewpoint, I am taking the column viewpoint, I am not taking the row viewpoint. What is the difference between row viewpoint and column viewpoint? We'll come to that at some point later. Okay, so now I have two possible solutions. I have one solution which is x1. So I would write this as 2 minus 1 0, and I have x2 which is 4 0 1. Okay, I found two possible solutions, but he claims that there are infinite solutions. How do I get two infinite solutions?
Linear combination of these.
Span of that.
Any linear combination. Any linear combination. So, if I construct a vector which is alpha times 2 minus 1 0 and beta times 4 0 1, just check. This also will be a solution, because a times this vector is 0 plus b times beta times this vector is 0. So, two solutions add to 0. So any vector which is, what do I mean by any vector which is,
Span.
right? So what I want to say here is that the solution lies in the span of these two vectors. So solution, are these linearly independent?
Yes.
These are linearly independent, and then solution lies in the span of these two vectors. What is the dimension of the space created by the span of these two vectors?
2.
Because there are two linearly independent vectors, all possible linear combinations of these two vectors will give rise to a two-dimensional subspace of 3 dimensions, R3. Okay? Will give rise to a two-dimensional subspace of R3. Okay, so span is something which you have been using without knowing what is happening. Now let's graduate from these examples to differential equations. Okay, so that we get the feel of how we can generalize these concepts to some other spaces than what we have been looking for. Okay, so my third example, I already covered two examples. So third example is not Ax equal to b. Well, conceptually it's not different from Ax equal to b, but it will take some time to realize that what I'm talking about is one and the same thing. Okay, let's look at this particular example. So now I want to have a transition to an example which is different. from linear algebraic equations. I am looking at differential equations. Well, this equation is not too different from Ax equal to B. A here would be this operator, differential operator, operating on vector u and giving me 0 vector. Okay, giving me 0 vector. So this is exactly like Ax equal to 0, except I have to write as d3 by dz cube plus 6 d2 by dz square plus d by plus 11 d by dz plus 6. This operator operating on uz is equal to 0. Actually 0 is the 0 vector in this space. What is this funny space? I have not talked about it earlier. This is set of thrice differentiable continuous functions. Set of thrice differentiable continuous functions on interval 0 to 1. So z belongs to, this is a set of z belongs to 0 to 1, and this particular set is thrice differentiable continuous function. C3 0 to 1 is thrice differentiable continuous function. Well, you know how to solve this problem. I have not given initial conditions. I want to get a general solution. I want to get a general solution to this problem. How do you do that? You write the characteristic equation and then you write the solution. So let's what you already know. So the characteristic equation will be P3 plus 6P square plus 11P plus 6 is equal to 0, and then I can write P plus 1, P plus 2, P plus 3 is equal to 0. So there are 3 roots, minus 1, minus 2, minus 3, and then all of you know how to write the solution. But what I want to point out here is something different. I want to talk about a span. Okay? So the general solution to this particular problem is given by uz is equal to alpha e to the power minus z plus beta e to the power minus 2z plus gamma e to the power minus 3z. Okay? Look at these 3 vectors. Where are the vectors coming here? The vectors are 1, 2, 3. So this is my x1z, this is my x2z, and this is my x3. This is my x3z. Okay? The general solution to this problem, it belongs to span of all possible linear combinations. What will fix alpha, beta, gamma? Moment to specify initial conditions. Alpha, beta, gamma will get fixed. Well, if you have not done this earlier in your BTech, we will be doing these solutions a little later. This is linear combination of these 3 vectors. So I can say that uz actually belongs to span of e to the power minus z, e to the power minus 2z, and e to the power minus 3z. Okay? So so span is something which I need to know. Something that I need to know. If you remember, there are 2 solutions to a problem of this type. If there is something on the right hand side, right? There's something on the right hand side. If there's a forcing function, then you have a particular solution, and you have the general solution, which is the general solution will be this. There will be a particular solution depending upon the forcing function. The general solution is actually governed by initial condition and span of these characteristic vectors. Any solution which is where forcing function is 0 will always lie in the span of these 3 vectors. It cannot leave this. solution of this cannot reach this subspace. What is this? This is a this is a subspace. Right? Is it a subspace? It's a subspace. All possible linear combinations of these three is a three-dimensional subspace. What is the underlying space which we are talking about? The underlying space which we are talking about is thrice differentiable continuous functions. Each one of them is thrice differentiable. Do you agree? All of them are thrice differentiable. Okay? First of all, I want you to understand that matrix A operating on a finite dimensional vector x giving me 0 and this operator operating on this vector belonging to this space are not fundamentally different ideas. They are same things, geometrically same things, nothing different. If you start viewing, yeah.
So how can we visualize these as vectors like we used to minus z?
As I told you that you cannot visualize these spaces. You can visualize only in 3 dimensions. But believe me that if you understand in 3 dimensions what is happening very well. Okay, we talked about a 2-dimensional subspace of R3 just now, right? Okay, in the same sense, see what is a 2-dimensional subspace in R3? Is it a very thin set? There are too many vectors in R3, right? And then R2 is a plane passing through the origin. It's a very thin set. There are fewer vectors relatively. Smaller infinity than this bigger infinity, right? Now, in the same sense, well, I can construct vectors in this space which are, minus 2, minus 3, minus 4, minus 5, minus 7. All of them belong to thrice differentiable continuous functions. Right? Actually, we will come to this idea of basis, and what we'll show is that this particular space is an infinite dimensional space. There are infinite vectors in the spaces. Linearly independent vectors that you can find in this particular space are infinite.
Had the right hand side not been 0, this would not have been a subspace.
Which one?
The solution?
No. You will get a specific solution the moment I specify an initial condition. If I specify initial condition u0 is equal to something, say alpha, not alpha, I'll take A, and then u dash 0 is equal to B, and u double prime 0 is equal to some C. Moment I give you these 3 initial conditions, these are some specific numbers. You can take minus 1, 2, minus 3. I have taken some arbitrary numbers. Okay. Moment I fix this, okay, I will get one specific value of alpha, beta, gamma. I'll get one specific value of alpha, beta, gamma, which is one element. Okay. Now, if I change the initial condition, what will happen? I'll get another value of alpha, beta, gamma. Okay. But all of them have to belong to.
Sir, but if the right hand side of the main ODE had not been 0, then 0 vector would not have been in the span, then it would not have been a subspace.
No. When you have something here, f of z, how do you solve? There are 2 solutions. One is the characteristic solution, this part will anyway appear, plus something will appear here. So this part is invariant, whether there is something on the right hand side or there is nothing on the right hand side. Right hand side can be 0 vector, can be non-zero vector. This will appear all the time. So some part of the solution will always belong to this subspace. You cannot escape it. This is characteristic of this particular equation. Okay. So these three vectors are kind of married to this equation. Okay. This can change. The right hand side can change. This can be sine, cos, whatever. This forcing function can be different. Okay. But this is something like inherent nature of this differential equation. You cannot change this. That will change only if you change these coefficients. Okay? It will change only if you change the coefficients. Okay, so this is fine. Let's move on to another example, which is again differential equation, and it will sort of preempt what I am talking about as dimension that I have not yet introduced formally what is the dimension of a vector space, but this particular example will lead you to that idea of dimension. Well, there is one question. These three vectors, are they linearly independent?
Yes.
Why?
There's no scalar multiple.
No scalar.
You have to prove it. So I should prove that alpha e to the power minus z plus beta e to the power minus 2z plus gamma e to the power minus 3z is equal to 0.
Has no solution.
Actually, which means 0 function. 0 doesn't mean 0. 0 means 0 function. Can be found only when alpha, beta, gamma are 0. So these are linearly independent. Okay? Can you prove it? Well, I'll leave it to your. There's one example which is here. I don't know whether I'll get time to do it, but you should look at this example. This short example in my notes. How do you prove that these three vectors are linearly independent? It's not that straightforward. You have to do some amount of thinking. Okay, let's move on to this fourth example. So my example 4 is a boundary value problem now. So I have two boundary conditions. This is the differential equation which is satisfied in the domain z going from 0 to 1. Okay. Then I have this boundary condition at z is equal to 0. So this is u0 is equal to 0, and then I have a second boundary condition at z is equal to 1. So this is u1 is equal to 0. Well, this kind of problems will appear when you start solving partial differential equations, and so-called strong linear theory, which will be covered in the other course. So, or you might have seen this in your undergraduate. These kind of problems we visit in heat transfer and mass transfer once in a while. Uz is equal to alpha 1 sine pi z plus alpha 2 sine 2 pi z. Well. The general solution here cannot be expressed in terms of finite number of vectors. For this particular problem, a general solution cannot be arrived at by taking only finite number of vectors. What are vectors here?
Sine pi z.
Yeah. So this is my x1z. This is my x2z. This is my x3z, and so on. How many such vectors I have? Infinite. I have infinite vectors. Okay. Where does the solution belong to?
Space.
Span of? What is this? This is linear combination of vectors. Linear combination of vectors, right? Same idea which was being talked about earlier. Take a set S. Okay. What is the underlying space here?
C2.
Somebody said it. C2. C201. Okay. The underlying space here is C2. Well, you have to be careful when you write this notation. It has to be square brackets, because two ends are included. There are two boundary conditions, not just. So twice differentiable continuous functions on interval 0 to 1. That is the underlying space. Okay. So where does this solution belong to? Solution belongs to the span of. These are vectors. These vectors belong to twice differentiable continuous functions. Okay, a linear combination of them gives me a solution to this problem. Okay, infinite linear combination, not just one value. These, well, in a partial differential equation, these coefficients alpha 1, alpha 2, alpha 3 will be fixed by some other particular solution, which this comes as a coupled problem in the partial differential equation. So there will be one part of the partial differential equation will be solution to this problem, and the other part will be particular solution. So that is, you can look at the book by Professor Pushpavanam if you want to mathematical methods in chemical engineering. That will tell you how these solutions appear. But the point that I want to make here is that UZ actually belongs to the span of span of this set of vectors. Belongs to span of this set of vectors. So span is a very, very important concept that we keep requiring everywhere, not being introduced just for the sake of it. Okay, in this particular case, the space or the subspace of twice differentiable continuous function, which is defined by these vectors, okay, is infinite dimension. Okay, because these are linearly independent vectors. Well, coming to a point where we have to define what is linear independence, and then we have to also worry about the basis business. Is this clear? Are these 4 examples clear? Somebody has any doubt? Please feel free to stop me at any point. Is it possible? Well, if you take initial condition, it depends upon the initial condition. So if you take initial condition to be 0, 0, 0, only possible solution that you will get is depends upon what is the initial condition of u0, u prime 0, u double prime 0. If all the 3 initial conditions are 0, 0, 0, alpha, beta, gamma will be 0. Yeah.
So the elements of this function space C2, sir, are they the functions or the value of those functions?
No, they are functions.
They are the functions.
They are functions. They are not value of the functions.
So then why do we need to specify 0 to 1 or any limits for that?
0 to 1 in particular problem, this particular problem would be a heat transfer problem. It will be something like conduction in a rod. 0 to 1 comes because you non-dimensionalize the space variable, and 1 is, it could be 0 to L if you want, doesn't matter.
Sir, why the limits? Why can't we just say C2?
Well, if you, no, these are different spaces. You may have a situation, see, there are some problems in physics or in chemical engineering where you have some infinite dimensional rod and etc. Right? So you may have a scenario where you have space which is C2 minus infinity to infinity, or C2 0 to infinity. But these are different spaces than this. This space is different than this space.
But the elements are same.
No. A function defined over 0 to 1 is not same as function defined over 0 to 5 or minus pi to pi. They are different functions. There is some part which is not included here. Okay. They are not same.
And it will not even be continuous, sir.
Huh?
It will not even be continuous in some other region.
Exactly. That is another problem. It may not be continuous. It might be continuous in some region, but not continuous in some other region. So all kinds of difference. Okay, let's move on to this basis and dimension business. So now, what is basis? What is dimension of a space or a subspace? Okay, the formal definition of linear independence that you will find in the notes. So we again define abstract terms. We start with this set S, which is set S. Okay. Zero vector Well, when I'm writing 0 on the right hand side, it means 0 vector in that particular space. So because now, if these vectors are n dimensional, what will be this 0? Well, let me qualify it by putting a bar over it. 0 bar, it is 0 vector. Okay, 0 bar is 0 vector. So if this is equal to 0 bar, then it's 0 vector in that space. If it is function space, set of continuous functions over 0 to 1, what is the 0 vector?
0 function.
0 function everywhere. Okay, fz is equal to 0 on 0 to 1, that is a 0 function. Okay, so that's what it means. It doesn't mean numerically 0 at one point, depends upon what space you are looking. Okay, so if there exists a linear combination such that if there exists a non-zero linear combination, which yields a 0 vector, which means if I can find some non-zero elements alpha 1, alpha 2, which will give me 0 vector, then these elements are linearly dependent. Else they are, if you cannot find a non-zero combination, which means only way to get a 0 vector is to put alpha 1 equal to 0, alpha 2 equal to 0, alpha 3 equal to 0, alpha n, all of them are 0. Okay, then they are linearly independent. Then the set of vectors is linearly independent. Okay, and what is basis?
Linearly independent vectors which generates x.
Yeah. Basis of a vector space is nothing but the set of linearly independent vectors which generate the entire space. Minimal set. Okay, which generates the entire space. So the minimal linearly independent set, which generates the entire space. Yeah.
Sir, why minimal? Because
I can in 3 dimensions I can take 4 vectors whose span can generate the entire space.
Sir, but they won't be linearly independent.
Huh?
They won't be linearly independent. One will be dependent on 3.
Yeah, the minimal set. Okay, the minimal is not really required. The linearly independent set, which generates the entire space. When you say entire space, actually it's the minimal set again. So, when do you say that a space has finite dimension?
It has finite elements in.
The number of elements in the set is finite. Okay, number of elements in the set is finite. It's called a finite dimensional space. If the number of elements in the basis set, the number of linearly independent vectors in the basis set is infinite, then it's called infinite dimensional space. We saw one example of infinite dimensional space just now. Linear combination of sine pi x, sine 2 pi x, sine 3 pi x, sine 4 pi x, infinite. Okay, all these vectors actually form a basis. And we can show that they generate the entire subspace. Okay, the dimension of that particular subspace is infinite. Why? Because number of linearly independent vectors. You cannot find a combination which you cannot find a non-zero combination which will give the sum of all those vectors equal to 0. Linear combination of those vectors to be equal to 0. So that means the dimension of the space generated by sine pi x, sine 2 pi x, sine 3 pi x, sine 4 pi x is infinite. Okay. So we started with 3-dimensional spaces. All that we are doing is just trying to generalize ideas from 3 dimensions. Just remember that. We're just trying to generalize ideas from 3 dimensions. So, visualization, geometric ideas, you should be clear in 3 dimensions. If you understand 3-dimensional world very well, no difficulty in understanding all these infinite dimensional and n-dimensional businesses. Okay? So just be clear about your 3-dimensional geometry, and then that's enough. All visualization can be done using 3 dimensions. The concepts are just being generalized. So these grand generalizations will occur in mathematics in the period 1850 to 1950, in this 100-year period, and with these grand generalizations, you can actually have a very different view of engineering or applied mathematics. So you will see that you are just working with if you start having this viewpoint, then working with Ax equal to b in finite dimensions, or working with some boundary value problem or some differential equation is not different. Operators change, what you call as a vector change, what you call as b on the right hand side change. Actually the problem that we talked about, we talked about this problem of d3 by dz cube plus something 6 into uz. If I put this equal to some fz, okay, this is fundamentally not different from ax equal to b. Solving for ax equal to b in 3-dimensional spaces is same as solving for this equation in thrice differentiable continuous functions, set of thrice differentiable continuous functions. Fundamentally not different. It's the same equation, different space, underlying space is different. We are not doing something fundamentally different when you are solving this and solving this. Okay? The specific solution which I wrote was for f of z equal to 0. That's a specific solution. And then if you take some fz, whether you can solve this problem or not, that depends upon the span of the characteristic equation and so on. So it's the same idea which will apply here when you solve x equal to b. The same idea will apply here. So we'll continue in the next lecture with. This is not enough. This is not enough. We have just defined these spaces. We have defined span, linear dependence, basic business. We need to go further and say now when in 3 dimensions, I had something more important. I had length of a vector. Now how do I generalize length of a vector? And why generalize length of a vector? That is another thing. Because we will need to define something called convergence, limit, and so on. That's why we have to define structures like norm. We'll talk about it in the next lecture.